Today we are talking about throttling system design. I believe a lot of you might have already know about like what is throttling system, what it does. It's also called rate limiting. And the purpose is to prevent excessive access to the system to protect system from overload. Like peak hour traffic, normally we're expecting 2 to 3 times or even more than the normal traffic volume and or like prevent DDoS attack, which is I think a lot of public APIs are exposed to DDoS attack. It can also help to solve noisy neighbor problems in a multi-tenancy setup where one tenant might starve all the resources, make the resources not available to other tenant. It can also provide tiered quality of service, like we can differentiate from free layers to premium layers. And also, like in the case of downgrade service, we can make calculated choice about like what we do there. Also, it can handle different types of burst traffic. For example, there's a less frequent read like for large files, like a 2 GB data every 10 seconds. And also there are like small but more frequent requests like reading tens or hundreds bytes of data every few milliseconds. So it is quite useful to put some mechanism in front of your system to protect system from overload. And there are normally like two ways of implement that, about where like we can do it on client side or we can do it on server side. So client server. So the client side doesn't really mean like it's a customer facing on the website or app. It can also mean like backend servers or services. It can have a record about like what kind of traffic it exposed or sent to the downstream services, and so they can take control here from the client side. But most commonly, it is implemented at the server side because the service will have different types of metrics to know, like, hey, how can I adjust dynamically, or how do I know like the system health? It has more information, have more control about the situation. But in large, like for example, in cloud environment, maybe there's a lot of times there's a combination of both. There are some simple mechanisms on the client side to prevent uh, overloading the downstream services. But in most cases, like 90% of the time, it's implemented on the server side only. And talking about throttling, that always came the topic about the algorithm to manage the throttling solutions or middleware. I'm just going through like two most common or most popular ones. The rest of them, like there are so many available resources you can find online if you want to get more familiar with that. The first one is definitely the token bucket. It is implemented with a lot of large systems. And it is quite simple. You have like as the name suggested, you have bucket. The bucket has a given size. Let's say for simplicity, we're just saying maybe 6 tokens. So when the request comes in, maybe let's put a middleware somewhere. Uh, Throttling, middleware. It will check if there is enough token in the bucket. And if there is, it take one and pass the request to the server. That means the server is available. And as you can see, if the requests keep coming, bucket keeps being removed from the bucket. Then we need a second thing to refill the packet at a certain rate. So that comes a concept about refill. Normally, it's decided by seconds or milliseconds. Like in this case, we can make it simple. So every second, we refill like two uh, token to the bucket. So that means, so for every second, we refill with two tokens. And then, as you can imagine, this create like a mechanism to prevent the server from taking excessive workload or request from the client side. And this looks simple enough if it is a single server instance. And also another popular ones, yeah, especially useful like for like single instance or the small cluster setting up. It's called like leaky bucket. So this token bucket and leaky bucket. For some reason, I do not think the leaky bucket is a proper name. You'll see why. So same thing or similar, it is implemented in the queue way. So like it's like a certain buffer or just like any queue processings, you have a buffer up front the server and the middleware will check if there any space in the queue. For example, maybe these two are failed. What I failed? Yeah, let's say these are failed. Now it has three places left, so it can pass the request to the server, just like we do for the token bucket. Or if the queue is filled up, like imagine it's all filled up, the excessive request will be dropped. So as you can see, if there's a burst of request, it can fill the queue immediately, and then it will be processed one by one, and that means the new request will be all be dropped. It will like keep processing the stale data. So I think that's the most significant reasons. Is not like well or most common algorithm. Of course, like Shopify notionally using this mechanism, but I think it's because their traffic pattern about like regular intervals. I believe most right is happening because it's the e-commerce website. It's happening at the checkout stage. So it is quite consistent so that they might fine tune the parameters to make it work for them. But for most generic or more common use cases, I believe the token bucket is like a more popular one. It is easy to implement, sufficient, only have like two parameters, and also it is more helpful in the distributed system environment. We can go in there in the next few minutes. And after the algorithm, and of course, there is mechanism. So in case like the request is throttled or like nearly to be throttled, we can have like a so-called back pressure mechanism. And can send the request in, then we can return if it's, for example, HTTP request, we can return with like HTTP response code 429, which means like too many requests. and will reject or refusing to accept like a new request. We can also use the different types of headers. Um, Most common one is like how many requests are left before you are going to be throttled, and let me find what's the actual name for that. Uh, yeah, I don't remember the name, but it's definitely like a number request left before started. Retry after. So we can set certain headers for the client to aware of the situation. This mechanism is called like back pressure. So at this stage, we are refusing to accept a request from the client. So now we are talking about like single instance throttling. We have the mechanism. Then we need to have a configuration, which is another important concept in the throttling system, also called throttling rules. This is like normally multiple levels in that either JSON format or other like well-known format. So normally it start at a service level, like service name, and then it can have like API level or either maybe the next level, different parameters that depend on your use case. Then the rules will be um, number of request. Maybe like 10 time unit would be 1 second. Every second time request is a request. So you can fine tune this configuration based on your requirement, and also it can be combined. For example, service level is the highest level, and then you can have like lower level configurations. And one, the throttling middleware trying to read, it can combine those. Of course, the lowest level or more specific level uh, rules is overriding the higher level rules. So for example, service level is like 10 requests per second, but maybe at the lower level at this particular API, it is at 5 per unit per second. So as a result, for this particular request, it will be like a file request per second as the rate limiting configuration. So normally the rules can be based on API, service, client, or different tiers like premium, auto count type, IP, etc. And normally the unit is either per second or per minute, depending on the actual business case and access patterns. And so normally for an issue, there'll be one specific bucket associated with that. The throttling middleware will be reading from the rules, checking the mechanism, either token bucket or leaky bucket, and then making the decision to send the request to the server or not. So for a single instance, that would be enough information. And as always, the complexity is increasing when we are talking about like a distributed environment. So there are some things still useful, like the algorithm still there, the configuration is still there. I think just how we handle that is slightly different. So I think maybe first thing we can talk about like the configuration rule handling, because currently it's not scalable. It's like one single configuration, maybe on a single server or in a local environment. But for large distributed systems, the configuration rules will be handled. Let's reuse that configuration rules. And then you need for the middleware, let's say just shortly handler. As always, that won't be a single point of failure. So there's you can imagine so many instances of throttling handler, and they won't be reading from local storage. It will be globally distributed valuable data, and for fast access, we definitely need to cache the configuration rules. Normally, like this, it'd be a good place to save this information. This is one way. It's a centralized approach. Later, I can introduce decentralized approach. First configuration. So as always, we'll have a bunch of workers. To pull the configuration rules and send them to the caching, and then different throttling handlers can read from that. And this can be replicated for different cases. And also, this can include the checking for most case total bucket. The information will be shared, for example, one token bucket for a given service. And the service, of course, is not a single instance. It's one instance one. They may even sit in different data centers, availability zones, wherever, and it will read Throttling handler or middleware will read the configurations, will read the current situations before deciding to send the request forward to the service cluster or not. And on the local service side, there's two strategies we can use. One is sidecar mode, one is library mode. Sidecar mode is we can't modify the service directly to implement the library, where it handles the throttling configurations, upload the current situations about the service, about the server, is it overload or not, etc. Sidecar mode is a long running process. in the Unix world or Linux world, it's about like a long-running daemon process to take the traffic, take the command and forward it to the service, or like it can also like upload the local service and server informations back to the Throttling handler for it to make a calculated decision. So that would be one way of doing that in the distributed world. Because it's not always like the set rules, it can make sure like we have like dynamic rules to config. And talking about dynamic rules, normally we would have a portal for manual intervention. Like in this scenario, we want to change the rules because we see the traffic from dashboard or just from administration. We want to change some rules, and then we need to make sure the rules are changed can be picked up quickly by the workers. So there are different mechanisms here. We don't want to go into too much details, but you should be aware there is manual intervention is available for the rules, and workers can update those accordingly. And different throttling handler or middleware, they can pick it up quickly and making calculated decisions. So this part, I don't see like it is covered by any other interview preparation materials, but just to bring awareness, we can have a deeper discussion if you want. Leave me a message, we can have a session together. So this is like what I call the centralized approach for manage throttling in a distributed system. And in the extreme cases, we're talking about AWS level or Google level in the cloud environment, a billions requests per day. Using Redis may not be as efficient as it sounds in a smaller scale. So in that case, that won't be work. We need to remove that from our system to achieve even higher scalability. So we will be still having throttling handlers, throttling managers, I say. They will be managing the throttling configuration, throttling mechanism together, and then they will be connecting with each other through what? Drum roll 3, 2, 1. Through P2P protocols like gossip is the most popular one. So each manager will manage their local copy configuration rules, manage their like token bucket availability, etc. They will communicate with other managers through P2P protocols to propagate any configuration changes, any data exchange, or checking the house to make sure they are still working or they can make decisions if they are not. So that's a typical P2P network for extreme efficiency and scalability, and the rest remains the same. They are managing configuration, SSH use, and algorithm. In, and any service instance, either through sidecar or let mode, they can take the configuration or the throttling rules, throttling decisions from any throttling manager. And you can also communicate with throttling manager to upload service information, server information for them to make decisions. And in case the throttling manager is down, it will be passing just like any P2P system, like consistent hashing rings. They can contact other managers in the case of service down. And also it can save like a local caching report. Local caching strategies. In the case it lost the connection to outside world, and make sure there's still the alternate mechanism available. Maybe not the most efficient or most up-to-date one, but still is better than nothing to protect the system. And as you can imagine, if we're talking about P2P, why not make sure the two instances talking to each other? They can share information to make sure neither of them are overloaded. And they can save some traffic between the service instance to the manager. So yeah, it's really complex if you want to do it right. And if you really want to dig into that, let me know. We can go through that. But as long as you're aware, there's different mechanism to do this, and there's complexities in the throttling, even for the throttling system, which may sound simple enough and easy to implement. It has a lot of nuances in here. And also, after everything is implemented, the next task is not, as always, it's not drop down. You need to continue monitoring and fine-tune the system to make sure like two side. First side is about the rule configurations, how efficient they are. If it works well or not, is too many traffics are throttled or rate limited, or is you are still seeing overload that you can fine-tune the rules. The second part is about like algorithm, how efficient they are. You can fine-tune the parameter as well to improve the performance, etc. So that's a continuous process. So hopefully you have a good overview of throttling system from single instance in a distributed environment for centralized throttling management and decentralized. So that's an overview for throttling. In the next session, we can go a little bit deeper on about a P2P network, which I briefly mentioned here. It's a quite interesting concept for the extreme high requirement for performance and for scalability. So I'll keep you tuned. All right. Thank you very much for watching. I'll see you next time.